there are a couple nice special cases that make integrating certain functions much easier. So these are basically tricks or shortcuts for integrals for these special cases. You never have to use these shortcuts, but these shortcuts can be kind of nice. So, let's see what they are. They're for integrals involving functions that are odd and even. So just as a reminder, an even function is a function that satisfies this equation. So f of x equals f of minus x. And on the graph of a function, an even function is one that's symmetric across the y-axis. So for example, think of the function x squared. Right, that's like this. And if you flipped this across the y-axis, the picture would look exactly the same. So this is what an even function looks like. So something like this, that's an even function. Even something like this is an even function. Right? As long as if you flip it across the y-axis, it looks the same. So let's take an even function and imagine what the effect of it being even would be on a definite integral. Well, a definite integral is talking about areas. So, right, if you do some sort of definite integral, you end up with, say, this area. But on the left-hand side, because of the symmetry of the graph, there's a region that's exactly the same. So these two regions are going to have the same area. What would that mean for a definite integral? Well, let's say that this x value out here is, I don't know, let's call it a. By symmetry, that means this x value over here is minus a. So if you have if you have an even function, all of the area here is going to be the integral from minus a to a of f of x dx. But what we just noticed is because it's made up of these two equal pieces. So all of the area is actually twice one of these two pieces. Let's write down the piece on the right just to be concrete. So twice the integral from 0 to a of f of x dx. So that's a nice little shortcut for even functions. If you're integrating over from minus a number to plus the same number, what you get for an even function is just twice of integrating from 0 to the top number. If you actually work out the integral, right, you don't need to use this formula to figure out these integrals, but often it's easier to have 0 as one of your bounds than to have some number. So this shortcut can save a little work because it's usually easier to evaluate your antiderivative at 0. So that's how it works out for even functions. What about odd functions? Just as a reminder, an odd function is a function that satisfies this equation, so minus f of x equals f of minus x. But on the graph, an odd function is one whose graph is symmetric about the origin. So as an example, think of x cubed. Right? It looks like this. And if you spun this picture 180 degrees around the origin, it would look exactly the same. Another common function that is odd is sine. Right? Sine looks like this. And if you spin that graph around the origin 180 degrees, you get the same graph. So sine is an odd function. So just like we did for even functions, let's think about what sort of effect this would have on a definite integral. So here's an odd function. Let me draw that a little more carefully. Okay, still not great, but we'll go with it. So imagine, let's look at this graph and think about what sort of areas, what sort of regions a definite integral would measure. Well, if you started it at 0 and did some sort of definite integral with this odd function, you'd get this wedge shape here. But there's another version of this wedge shape. It's actually to the left, down here, right? That's exactly the same shape because of the symmetry of the graph. But the region on the left here, it's below the x-axis, so it would count as negative. And this region on the right that's above the x-axis would count as positive because it's above the x-axis. If the one on the right were below the x-axis, then the one on the left would be above. So there's these two regions are the same size because of symmetry, but also one of them is positive and one of them is negative. And that means that if you add these two regions together as signed areas, they're going to cancel. Well, the signed area, so let's name these x values. Let's call this one a and down here negative a again. The total signed area here, that's the definite integral from minus a to a of f of x dx. But we just said that because of the symmetry, these two regions are going to cancel. So this is going to give us 0. So for an odd function, if you integrate over an interval from minus a number to plus the same number, you always get 0. It could be any odd function, not just this particular one that I've drawn here. So even and odd functions have these really nice shortcuts for definite integrals, although there is a big caveat, which is the interval that you're integrating over has to be from minus some number to plus the same number. So let's look at a couple examples. All right, how about this integral from minus 2 to plus 2 of x cubed minus sine of x? Well, x cubed, that's an odd function. And sine of x, that's also an odd function. And if you add two odd functions, you get an odd function. So this integrand is an odd function. And we're integrating over one of these intervals that goes from minus a number to plus a number. So this integral, it's 0. There's not really any work to do. So that's a pretty nice shortcut. If we did evaluate this integral sort of the old-fashioned way, using the fundamental theorem of calculus, we would get 0 as our final answer, but it would take a lot more work. So you can see that if you're in the situation to use this shortcut, it can save a lot of work. Let's look at a second example. So how about this one? The integral from minus 4 to 4 of x to the 2/3. So it's a little harder to tell if this is even or odd, but in fact it is even. It's even basically because of the squaring there. That kind of forces it to be even. If you looked at a graph, it would be a little more apparent that it's even. The graph of this function looks like this. Okay. So we can use our, because we're integrating from minus 4 to plus 4, we can use our trick for even functions, or our shortcut for even functions. And instead of integrating from minus 4 to 4, we can integrate from 0 to 4, and then just multiply our result by 2. So we're going to integrate from 0 to 4, x to the 2/3 dx. So you can see, unlike with the shortcut for odd functions, this one you do still have an integral to do, but usually it's easier, or at least evaluating it is easier because you get to plug in 0 at some point. So 2 times, so our integral, the power rule for integrals, we have to increase the power by 1, so that's going to give us 5/3. And then we need a 3/5 down here. Evaluate from 0 to 4. So 2 times 3/5 is 6/5. And then we'll plug in our bounds. For our top bound, we get 4 to the 5/3. And then when we plug in 0, we get 0. So this whole thing turns out to be 6/5 times 4 to the 5/3. And if we wanted to, we could get a decimal approximation for this by dumping it into a calculator. Okay, final example here. Let's find the integral from minus 1 to 2 of x minus 4x cubed plus 6x to the 5th. This function, this integrand function, it is odd. I can tell that it's odd because if you have a polynomial with all odd powers of x, it's an odd function. The same goes for even powers of x. If you have a polynomial that only has even powers of x, then it's even. If you have a polynomial with a mix of odd and even powers, it's not odd or even. But this one's all odd, so this integrand is an odd function. Unfortunately, our integral, the bounds for our integral aren't minus and plus the same number, right? They're different. So we have two options for how to proceed. We can either give up on using the trick and just evaluate this the old-fashioned way using the fundamental theorem of calculus, or we could split off, right? We could integrate from minus 1 to 1 and then add the integral from 1 to 2. Whether that saves any work or not isn't totally clear, but it's at least a possibility. This is one of those properties of integrals, that you can split up the bounds for an integral if you want. And the integrand for both of these is the same, x minus 4x cubed plus 6x to the 5th dx. Now for this first integral, we have an odd integrand, and now the bounds are plus and minus a number, so integrating an odd function over a symmetric interval gives us 0. So that makes that very easy. So we only have this integral to evaluate. Of course, this integral isn't really that much easier to evaluate than the one that we started with, but oh well, such is life. So let's write down an antiderivative. 1/2 x squared minus x to the 4th plus x to the 6th. And we're going to go from 1 to 2. So plugging in 2, we get, let's see, 2 squared is 4, over 2 is 2, minus 2 to the 4th is 16, plus 2 to the 6th is 64, minus, and then plug in 1. So 1/2 minus 1 plus 1. So these cancel. So let's see, 2 minus 16 is negative 14, plus 64 is 50, minus 1/2, so 49.5. All right, so for this one, using this trick, I don't think it really made things any easier. But it's sort of neat to see that you can split up the interval of integration and still use the trick if you really want to.